Good afternoon, ladies and gentlemen. Welcome to the Prague International Seminar on Function Spaces. Our today's speaker is Giuseppe Rosario Mingione from the University di Parma in Italy, and his talk will be about perturbations. The stage is yours.
Unmute. Okay, I can start right now. Okay, thanks for this invitation. I'm happy to give another talk at this seminar because actually by browsing the history of this seminar, I realized that I gave a talk here at this seminar exactly 20 years ago in 2002.
664913. Hello?
I mean, someone should okay, exactly. I gave a talk at this seminar 20 years ago. I think at that time it was organized by the Czech Academy of Sciences or whatever. I don't remember, but it was 20 years ago. Now it's okay. And it's a pleasure to be here again. So it's perturbation beyond Schauder. So it's actually about a recent paper that I wrote with the Cristiana De Filippis from Parma, and this paper contains the long-awaited extension of Schauder theory to the class of non-uniformly elliptic operators. Okay, let me start from different notions of non-uniform ellipticity. Okay, what I'm going to talk about is essentially regularity of minimizers of integral functionals of the calculus operations of this type and related equations in divergence 4. And of course, the catch is given by the Euler-Lagrange equation of the functional, which is this one, which is satisfied by any local minimizer, and it is exactly of the form in the second display. Okay, how do we say that this operator is uniform, is elliptic? By prescribing that this matrix is positively defined, and then we give two measures for the lowest and the highest eigenvalue. And we describe this lowest and highest eigenvalue with two functions, two positive functions, G1 and G2. And in the case of functionals, this translates into this. And in the autonomous case, it is commonly used a couple of functions, G1 and G2, that are not depending on X. So this is just to measure ellipticity and growth of lowest and highest eigenvalues. Okay, uniform ellipticity in the literature means that when Z gets large, this ratio, called the ellipticity ratio, stays bounded uniformly with respect to X. And essentially, in the case this matrix is symmetric, that always happens in the variational case. This means that the ratio between the highest and the lowest eigenvalue is uniformly bounded. And there are actually different notions. Here I'm going to consider only large values of Z for reasons I'm going to explain in a few moments. Okay, these conditions, let me just tell you that have nothing to do with degeneracy, because there are degenerate operators, like for instance the P-Laplacian operator, which is degenerate and which is still perfectly uniformly elliptic. This is a classical P-Laplacian, and that's actually why the classical Uhlenbeck theory works, because this is a uniformly elliptic operator. And it has nothing to do with non-degeneracy, which is usually prescribed by saying that the lowest eigenvalue never disappears, never vanishes. Okay, actually, there are many types of uniformly elliptic operators. They do not have to have necessarily p-polynomial growth. For instance, if you do consider a nonlinear perturbation of the Laplacian, you put a coefficient that depends on the gradient itself, and you prescribe this rebalancing condition involving the first derivative of this function tilde a, then provided this is true, then the operator is uniformly elliptic. It's still uniformly elliptic. So no polynomial growth is prescribed here, but still you are in the realm of uniform ellipticity. And these operators have been studied at length by many authors, and in particular, Schauder estimates have been proved by Lieberman in a paper in a famous paper by 1991. And this is just a very short list of people who recently worked on this topic. Okay, this is okay. What about non-uniform ellipticity? Classically, this is defined by saying that there should be at least one point where this ratio doesn't stay bounded, where z goes to plus infinity. So why the behavior at plus infinity is important? Because whatever you do when proving regularity estimates, you meet this ratio, and this ratio stays. If this ratio stays uniformly bounded, then you can perform a lot of estimates. On the other hand, the focal point, one of the focal points of the theory is that you want to prove that the gradient is locally bounded, and then you use that this quantity is bounded. But on the other hand, there could be, if you want to exclude that the gradient gets unbounded, then you lose control on this quantity, and so there's a competition. The gradient tends to be unbounded, this quantity tends to be unbounded, and then the estimates deteriorate, and then there's a competition between the two. Handling this competition means handling non-uniform ellipticity at its strength. Okay, and okay, similar definitions also occur in the case of non-divergence form equations, but this you can easily imagine. I will not spend time on this because I'm not dealing with these kinds of equations. Okay, this is a classical topic. This is a certainly not very extensive list of classical contributions by main authors. This is before the 70s. In particular, but there are even, I mean, even earlier ones, especially because the minimal surface equation is one prototype of non-uniformly elliptic equation, and in particular, there's been a lot of work in the Russian school in St. Petersburg, starting from Lagichenski and Duryaltseva, while in the States there were people like Finn, Gilbert, Severin, and Tudinger, whose thesis was exactly on this. There's also a deep paper by Leon Simon connected to minimal surfaces operators. These are more recent papers, and in particular, there are very interesting examples of non-uniform ellipticity cooked up by Zhikov, and there's a monograph by Ivanov that summarizes a lot of work made in Russia, and then there are these fundamental papers by Marcellini, who gave an extensive treatment of non-uniform ellipticity, catching conditions that were unachievable before. These are a few examples. This is a famous paper of Lagichenski and Duryaltseva on the topic. Essentially, there are also extending properties of minimal surfaces here. And these are papers related to Tudinger's thesis. And this is Leon Simon's paper I was talking about before. So just a few examples. Okay, and of course, if we translate non-uniform ellipticity in the variational setting, then this means that there should be at least one x where such that this quantity goes to plus infinity. So you lose control on this quantity that essentially enters in all regularity estimates. Okay, so there must be a competition because the gradient tends to be unbounded and this quantity deteriorates. So the standard assumption in the literature, whatever you do, is to prescribe one of the standard assumptions in the literature, at least the most standard assumptions until these papers of Marcellini dealing with fast growth conditions. But this is the classical condition that has been considered, is that this ratio blows up as a small power of the gradient. And you need it to be small, otherwise this competition resolves in unbounded gradients. In particular, this is usually formulated by prescribing that the lowest and the highest eigenvalue growth with different powers, so that the ratio is bounded by z to the q minus p, and then you want that this difference is suitably small. In this setting, this is exactly the setting of Paolo Marcellini's papers. where he introduced in the setting of cavitation, he gave a very interesting model of cavitation in the 80s, where he considered functionals growing with coercivity slightly smaller than boundness exponent, and then if you scale these growth conditions on the level of second derivative, you recover this one. And this is done by Marcellini in the setting of models for cavitations that, in my opinion, should be reconsidered, because the clever idea of Marcellini was to describe the cavitation phenomenon via an appearance of a certain term describing the presence of Lorentz phenomenon. So he introduced a relaxed functional, and in the relaxation procedure from an integral functional, you come up with a measure, which is actually a Dirac measure, and describes cavitation. This is let's say, a sophisticated way to look at cavitation that should be probably relooked at these days. Okay, and as I told you, this assumption prescribed that delta is not very large, and this means that Q and P cannot be too far apart from each other. And in fact, there are classical papers by Marcellini and counterexamples by Giaquinta and Marcellini that tell exactly that you get regularity of minimizers provided Q over P, which is usually called the gap, is not too larger than 1. It's 1 plus something that goes to n, typically like 1 over n. So it goes to 0 and then goes to plus infinity, and Q over P tends to be closer and closer to 1. The best optimal bound is not known for the gradient. This is just a sample of recent interesting papers that are investigating new conditions, new bounds. They're all of the type 1, a constant over n, and the only optimal bound is being found by Hirsch and Scheffner, because the optimality for the boundness of U but not of the gradient is confirmed by Marcellini's counterexample from the 80s. Then there is this interesting recent paper by De Filippis, Christensen, and Koch that should be finished, as far as I know, in a few weeks, months, I don't know. Okay, now I would like to go beyond this classification, and I would like to show you a further classification that it is, in my opinion, necessary if you want to study non-uniform ellipticity in the realm of non-autonomous functions. So when x is included in the integrand, then we should make a further difference in non-uniform ellipticity. So up to now, we have seen the pointwise ellipticity ratio. So you freeze the integrand at the point, and then you consider the ratio between the highest and the lowest eigenvalue at one point. And so uniform ellipticity, non-uniform ellipticity means that there exists one point where this goes to plus infinity. On the other hand, you could also consider this larger quantity. This larger quantity is obtained as follows. Now you don't take a point, you take a ball. So you delocalize the notion. You take the sup of the highest eigenvalue with respect to z when x varies in x, and over the inf on the same ball. You get, therefore, a new non-local larger ellipticity ratio. And this is a very useful quantity, because it's bound to detect milder forms of non-uniform ellipticity that occur and then create problems or new phenomenology, as I'm going to explain in a few moments. Okay, from now on, we shall say that, that an integrand is non-uniformly elliptic in the classical sense. Actually, if there exists at least one point where this ratio goes to plus infinity. She'll say that it's softly non-uniformly elliptic if it's pointwise uniformly elliptic. So you freeze and you get something which is bounded, but then you find at least one ball where the previous goes to plus infinity, where the no local ellipticity ratio goes to plus infinity. And we call it uniformly elliptic if this quantity is bounded. So this is essentially a classical definition. This is a classical definition, and this is an intermediate definition, which is necessary to detect more phenomena. And a discussion and this classification has been proposed in this recent paper with Cristiana De Filippis. Okay, let me give you one example that it's telling you that this classification is necessary. So this is a functional that I discovered in a few papers by Zhikov, and it's connected with nonlinear elasticity, homogenization, Lorentz phenomenon, and many other things. It's a simple functional, but revealing interesting phenomena. So how this functional behaves. So at those points where this modulating coefficient is 0, this is like a P Laplacian. Otherwise, if you freeze 1x, this is like a Q Laplacian plus a lower order term. But how larger it is, well, it depends on how large this guy is. So it's essentially, it mutates when A of x is larger or is 0. Now, let's see the difference between the pointwise ellipticity ratio and the non-local ellipticity ratio. Okay, if you do consider the pointwise ellipticity ratio, then you see that this functional is perfectly uniformly elliptic in the classical sense. So if we use the classical definition, this is pointwise uniformly elliptic. So at every point, this stays bounded, and actually the constant that you can put on the right-hand side is even independent of x is 0. So this looks like a uniformly elliptic functional or operator in the classical sense. On the other hand, if we take a ball where A of x is 0, and we assume that, of course, A of x is not always 0, and then you see that the non-local ellipticity ratio on this ball goes to plus infinity. So in this sense, this is uniformly elliptic in the class if we take the classical definition, but it's softly non-uniformly elliptic. So let me see why this classification is now necessary. If you would use the classical definition of non-uniform ellipticity, then you would expect that the minimizers of these functionals, then they share all the regularity properties that are typical of the uniformly elliptic case. For instance, Schauder estimates should hold, because this is pointwise uniformly elliptic. But there is this counterexample that is due to Irene Fonseca, Yamali, and myself, where we show the following, that we take this functional, we can also get a non-degenerate version of it, which is smooth with respect to the gradient variable. We take a Lipschitz boundary data. Perfectly Hilbert continuous coefficients. We take Q and P far apart depending on n and alpha, and then we take a minimizer which is nearly as bad as any other competitor, because any minimizer is obviously in W1P, so the set of discontinuity points of a W1P function does not exceed n minus P in Hausdorff dimension. So this is according to the classical definition, is a uniformly elliptic operator, but there are no Schauder estimates. So there must be another type of non-uniform ellipticity, and this is the soft non-uniform ellipticity that we were talking about. So this is a softly non-uniformly elliptic in the new classification. On the other hand, you can also say that here the central point, and actually I would like to recall, I would like to take the opportunity of recalling Yamali, was an extraordinary refined mathematician. I mean, this was an example that was exactly born in the following way. I had a construction of a one-point singularity, and I had more or less an idea how to distribute singularities. And then when I talked, I went to Pittsburgh, and in the Fonseca's office, I met Yamali, and he was extremely fast in understanding what I had in mind, and he came up with something called Ponomarev construction, and we were able to adapt this. So he had the real analysis tool at hand to realize this complicated example. But I have to say that he was an extremely refined mathematician, very subtle and deep. Okay, on the other hand, when Q and P are close enough, depending now this time not only on n, but on alpha, and please take a look at this ratio, alpha over n, then we were able to prove that U is locally Hilbert continuous, and this is the maximal regularity that you can expect. This was done with Baroni and Colombo in a series of papers that are displayed here. So we see that already for softly non-uniformly elliptic operators, Schauder estimates may fail, but there are also other conditions that ensure that this, let's say, Schauder, that the Hilbert continuity of the gradient works. So, and what I'm going to talk about in the rest of the talk is how to deal with Schauder estimates for general non-uniformly elliptic operators. Here there's an interesting list of papers, and in all these papers there have been progress on the problem of proving that the gradient is order continuous, but all these papers are for what we now call softly uniformly elliptic, non-uniformly elliptic operators. So in all these cases, and in particular, there are two very interesting papers by Peter Hester and Ji-Hoon Hock that I invite you to give a look at. And all these papers, they deal with the case that whenever you freeze, you get a uniformly elliptic operator. And what I'm going to talk about is what happens now in the hard case. So in the case when you have a pointwise strongly non-uniformly elliptic operator. So you freeze, and whenever you freeze, you still get a non-uniformly elliptic operator. You see, this is an integrand. You freeze, the C of x cancels, and then you get something that goes like z to the q minus b. So we are now going to Schauder estimates for the classical non-uniformly elliptic operator. Okay, let me now recall a brief what Schauder estimates are. Okay, Schauder estimates are essentially one of the two perturbation theories of elliptic equations. The other one being Calderon-Zygmunt theory, which is the other perturbation theory for elliptic problems. So we all know that solutions of these equations at harmonic functions are as smooth as you like. And the idea is that how much of this smoothness you preserve when you add coefficients that are, of course, supposed to be elliptic, so that preserves the nature of the equation. So the idea is that since the coefficient sticks to the gradient variable, then you don't expect that the gradient is more regular than what the external ingredient, that is the matrix A of x, is. That's what you expect. And that's the classical content of Schauder theory. So Schauder theory tells that if A of x is C0 alpha, then D is precisely C0 alpha, with the two borderline cases that turn out to be false. Okay, this is called Schauder theory, but the first who proved this statement in the interior was Hopf. The classical Schauder estimates that is up to the boundary with the sharp exponent were actually given by Cacciopoli, and then Schauder gave a proof in a more general case. So this is a classical from the 30s, and all these proofs are based on what you can actually expect. You freeze and compare. Then there are more modern proofs, and okay, the original proofs are based on potential theory and representation via fundamental solutions, parametrics. Look at, for instance, the papers by Agmon, Douglas, and Nirenberg. And more modern proofs have been given by Campanato. Campanato was the first to essentially trivialize this big theory and not to use singular integrals. Then there are clever proofs given also by Neil Tudinger and Leon Simon. And all these proofs require two things, that all the estimates are homogeneous, because you want to iterate these estimates, and turns out to be, at least with those methods, impossible to iterate estimates that are not homogeneous. That's the basic problem of regularity. You want to iterate, and in order to iterate, you have to, in a way or in another, iterate homogeneous quantities. And all these proofs, via blow-up, via let's say convolutions like Schrödinger or freezing like Campanato, they stay on the freeze and compare methods. And okay, for instance, let me see what Campanato does. So you're freezing a point. So you solve the frozen equation with the same boundary data of the original function. Then you prove this reference estimate that encodes the fact that dB is in turn Lipschitz. And then you prove the comparison estimates, which is, and here is the point and this is the point where regularity of coefficients comes into the play. And then, since these two estimates are homogeneous, you see square here, square here, square here, square here, then you can combine them and iterate them. That's the core point. Okay, the fact that these estimates are homogeneous is a direct consequence of uniform ellipticity. That's why for non-uniform ellipticity, all these techniques uniformly fail. And the same thing you can do in the nonlinear case. For instance, you can take the P-Laplacian operator, or even more general equations, and then you can add coefficients, then you can freeze coefficients, then you can use Uhlenbeck theory as reworked by people like Giaquinta Giusti, Di Benedetto, Manfredi, especially Giaquinta Modica, and then you can rearrange the same comparison procedure. But once again, you need that this equation is uniformly elliptic, and this is actually the case. Okay, a related problem I also want to talk about is another classical problem that has a more variational nature. So now, at this point, I'm not putting coefficients sticking to the main term, that's the gradient. I'm adding lower order terms, but with a difference in a functional, that this function h, which is written in blue, is non-differentiable with respect to the v variable. And so the Euler-Lagrange equation cannot be used since it just doesn't exist. And so you cannot use the standard techniques relying on equations, but still there are basic and classical by now papers by Giaquinta and Giusti that are able to bypass the absence of the Euler-Lagrange equation and use directly minimality to prove that the Schauder continuity of the gradient. And the same thing can be done when you add coefficients sticking to the main term, because essentially you are in the uniformly elliptic case, so the Giorgi's theory applies also to measurable coefficients. You still prove that B is a bit of Schauder, is bit Schauder continuous, and then you can readapt the previous technique. And once again, you don't use the Euler-Lagrange equation here because coefficients are non-differentiable. So let me summarize. There are two classical facts. The first is actually it's called non-linear Schauder theory. So you put a Schauder continuous coefficient and you want to retrieve Schauder continuity of the gradient. And the second is, let's say, a step behind. You put Schauder continuous coefficients, but you don't even have an equation, but still you want to prove that U is locally Schauder continuous. And these are two open problems. And the related open problems are the following. The first one is prove just already in this simple model case. So you get a non-uniformly elliptic operator in the sense that the ellipticity ratio goes like z to the q minus p as before, but still prove that adding Schauder continuous coefficients yields Schauder continuity of the gradient. And the second classical open problem, which has a more variational nature, is that do the same as before, as in the previous slides, but for non-uniformly elliptic integrants. So these are the classical facts in the uniformly elliptic case, and the classical two open problems in the non-uniformly elliptic case. And today I would like to describe the solution to both the problems recently obtained in a paper by Cristiana De Filippis from Parma and myself. So we solve both the issues, and the point is that we introduce a hybrid perturbation technique. Actually, it's we do not use perturbation. We just use a bit of perturbation, and the crucial point is to prove the L-infinity bounds of the gradient, because actually once you know that the gradient is locally bounded, then you don't have to worry about non-uniform ellipticity too much, because you already know that this ratio stays bounded and you have to adjust things. So that's the focal point. So as I told you, these are classical problems. They have been debated for some while. For instance, this is the classical paper of Giaquinta and Giusti, where they proved the Schauder, nonlinear Schauder theory when p is equal to 2 in the uniformly elliptic case. And in fact, the reviewer, that is Gary Lieberman, comments the fact that while these techniques work in the uniformly elliptic case, then these techniques do not work in the non-uniformly elliptic case. So this was an open problem that stayed there for more than 40 years, essentially because all these classical perturbation techniques fail in the non-uniformly elliptic case. Unless, of course, you don't assume first higher differentiability on coefficients, and second, that you already have a gradient bound. But if you have a gradient bound, the problem is not there anymore. So this is, for instance, one of the many places where this problem was discussed. And for instance, this is the monograph of Ivanov that summarizes this progress on non-uniformly elliptic problems made in St. Petersburg for all the 70s, 60s, and the beginning of the 80s. And in fact, he remarks once again that, the crucial point is to obtain a priori estimates for the gradient. If you want to treat, let's say, non-uniform ellipticity. So that's the crucial point. That's another point where this problem is discussed. And in fact, this is a theorem of Lagichenski and Dewey algebra for non-uniformly elliptic problems. And you see that they have to put two assumptions. First, that the gradient is bounded, and then that all coefficients are differentiable. So under these conditions, then you can prove that the gradient is uniformly bounded with the other conditions that we are also able to escape. So in our work with the Philippis, we get rid of these conditions. We essentially go to the real non-uniformly elliptic problem. These are the kind of classical open problems that I mostly like, because these days there are several so-called open problems that have been there for a few months. These are problems that have been there for several decades. And this is yet another point where this is discussed. This is from the paper of Giaquinto and Giusti this time, where they essentially observe the same thing, that they are able to use their techniques provided they already have a gradient bound. This is possible for a few special cases like a minimal surface operator, but in general, it's not there. Okay, and now let me go to the theorems of De Filippis and myself. So I start with a non-differentiable case. So I take a non-uniformly elliptic integrand with a term that cannot be differentiated. So this is non-uniform ellipticity, P different than Q, and this is non-differentiability. So it's just Hilbert continuous. Of course, if you don't assume either that is Hilbert continuous, the result generally doesn't hold. And under this bound, and this is in blue, is essentially a constant, as you see, because P is larger than 1. Under this bound, which is essentially up to a constant of the same form that we have seen before, and before we had the sharp bound Q over P1 plus alpha over n, which was for a special structure, then we can prove that U is locally Hilbert continuous. So nevertheless, we have non-uniform ellipticity. We are able to prove under, let's say, a standard assumption in the literature that U is locally Hilbert continuous. And we are also able to add intermediate terms where there is a more delicate interaction between the gradient terms and the B functional by reinforcing a bit. And so there's an interplay between the growth here, so that's the rate with which the intermediate terms affect the main term, which is the gradient, and the growth condition, and the bound on Q over P. Now we go to the realm of the real Schauder theory. So that's Schauder theory, that's nonlinear Schauder theory. So we have an elliptic, non-uniformly elliptic integrand, a Hilbert continuous coefficient. We reinforce the bound putting a square here, but the main quantity is the same, and then we still prove that U is locally Hilbert continuous. And that's, as far as I know, the first result in 50 years where there are finally Schauder theory, Schauder estimates for non-uniformly elliptic operators. I would like to say that 1 over 5 is to make it more readable. Actually, you can improve a bit this bound, making more delicate expressions, but the asymptotic remains the same. Of course, here we allow that the integrand is a bit degenerate convex, so we cannot hope to get full to have very good exponents, because otherwise there are counterexamples. But okay, sorry that there is something that doesn't move here. Enter full screen. Okay, now it's working again. Okay, let me go to the same place. Okay, this is what I was talking about, and as I told you, we cannot hope to get that U is locally heterocontinuous with the same exponent alpha, but in case the problem is non-degenerate, and this is a, let's say, a necessary assumption in light of the counterexamples for degenerate operators, then we are able to retrieve the classical results of Caccioppoli and Schauder for the non-uniformly elliptic case. So we prove we have a non-uniformly elliptic integrand with Hilbert continuous coefficients, and then you prove that the U is Hilbert continuous with exactly the same exponent of the coefficient. Okay, and now we go a bit, we escape the realm of Schauder theory because we also insert a presence of B. And in this case, we have to assume that P is larger than N, an assumption that we believe to be necessary, because otherwise the coefficients can be measurable, and there's no de Giorgi theory by counterexamples allowing for proving that that minimizers are Hilbert continuous with some exponent. There are counterexamples. And then we are still able to prove that U is locally Hilbert continuous. And you see that now this bound does not only depend on alpha over N, but also quantitatively on this assumption, because there is 1 over minus N over P here. Now we go, this is a brief summary of what I was saying before. In the classical case, we know that under these assumptions, B is a bit Hilbert continuous, and then we can go for the rest. In the non-uniformly elliptic case, Nottingham shows you this, and then by some analogy with the vectorial theory with the vectorial regularity theory, we have to assume that P is larger than N. That guarantees a bit of Hilbert continuity of minimizers. If you think of the classical Giusti-Miranda counterexamples, you see that in the vectorial case, you can have a linear functional with smooth coefficients, but if these smooth coefficients are depending on the solution itself, then still solutions are irregular. So that's the analogy. That's relevant analogy. Okay, what about for equations? For equations, now when you go to non-uniformly elliptic equations, then there is an ambiguity on the notion of solutions. You can have a distributional solution, but the notion of energy solution is unclear. Okay, an energy solution can be just in W1P, but can also be in W1Q and is more regular. So there are essentially 2 ways you can prove regularity theories. You start from an energy solution which is in W1Q, and this would give some, say, somehow a weaker result, or you go in the classical way. You solve the Dirichlet problem and you prove the existence of a solution which is locally with a locally Hilbert continuous gradient, as in the classical case. So we take the Dirichlet problem and we prove the existence of a solution that has exactly these properties. Then if the solution is also W1Q globally, then the solution is unique. But this is the most general case, and this is according to the classical theory in the literature. And in fact, in the literature, there are, it's classical in regularity theory, and that's why, for instance, in measure data problems, you have distributional solutions that are irregular, but if you catch special solutions, like, for instance, those introduced by Boccardo and Galloway, like the approximation, as also in this case, then you can prove some regularity for those solutions. And then there is a belief of some people that says that you can prove that that solutions are, distributional solutions are regular, no matter that they do not have good energy properties. For instance, there was something that Ibanez and a co-author of him from Italy conjectured, saying that we safely conjectured that distributional solutions that are not energy solutions to the P Laplacian equations are regular. I actually never understood why this conjecture was so safe, and in fact it was recently disproved by Maria Colombo and Riccardo Tione. And because it is, I mean, known in regularity that as soon as you escape the realm of energy solutions, then you don't have regular solutions. So in this case, in this sense, the approach of Boccardo and Galloway was the right one. I remember I listened to a few talks where there was some polemics between Lucio and Tadeusz, but actually I think that Lucio's approach was revealed to be the correct one. Okay, and for this case, we can prove exactly the same things. We can prove the same things, saying that if you have this bound, then we can prove that there exists a locally Hilder continuous, a solution with a locally Hilder continuous gradient in the interior. And if the equations are non-degenerate, we finally come to the classical Hopf-Schauder-Kaccioppoli theorem for equations. So this actually put a dot on a cast for Schauder estimates that has been discussed for many decades. Okay, these are theorems for the model case. In the general case, there is one obstruction for PQ growth functionals, and that's so-called Lavrentiev phenomenon. That's the inf over more irregular functions can be strictly less than the inf of a dense subset. And of course, if this happens, then minimizers cannot be regular by very definition of Lavrentiev gap. This is a clear obstruction to regularity. So what we do, we pass to the so-called Lebesgue-Serring-Marcellini extension that was introduced by Marcellini in the setting for describing cavitation in nonlinear elasticity. So what we do, we take the lower semi-continuous envelope of the, so we initially define the functional on W1Q, on the larger space. And then you take the lower semi-continuous envelope of this functional, which is defined on W1Q, but in the weaker topology. Then the Lavrentiev gap is defined as the difference between the original functional and this other functional, which is larger. Now, we always prove Schauder estimates for minimizers of this functional. So the difference between with the previous models is that this functional is not decoupled. It's a general structure. So we always prove Schauder estimates for these functions. Then if the Lavrentiev gap disappears, and this is a necessary condition for regularity, this implies that minimizers of the original functionals are the same of the relaxed one, and then regularity follows. In particular, this happens, the vanishing of this quantity, it happens for all the model cases we have seen before. So we first prove this general theorem. As a corollary, we get the model theorem, the model cases, and then we get essentially all the functionals you can treat. Because the only obstruction here is the occurrence of Lavrentiev gap. So if there's Lavrentiev gap, there's nothing to prove. Now, finally, a bonus section, because this is a seminar given, this is the Prague seminar, and in Prague there is an extremely strong function spaces school. Okay, it's just an extension of Schauder theory to borderline cases in a few situations. Okay, this is a classical Stein's theorem. It tells you what's the larger space the gradient has to belong to in order to guarantee by embedding that B is continuous. You know that if DD belongs to Ln plus something, that D is Hilder continuous, and the borderline space is the Lorentz Ln1 given by this function. These are, I mean, interpolation spaces. So by Calderon-Zygmunt theory and interpolation, you get the following reformulation of Stein's theorem. You want, and this tells you what's the largest space the right-hand side of the Poisson equation has to belong to in order to guarantee that the gradient is continuous. And this condition is sharp, as shown by Andrea Scianchi by means of counterexamples. Okay, a few years ago, we proved the following theorem, that we call the nonlinear Stein theorem. And we proved that if you take the P Laplacian operator, you had a right-hand side which is in Ln1, and a coefficient which is just Dini continuous, so it's a limit of Hilder continuous coefficients, then du is continuous. So there's no difference between, and this also holds for all essentially equations modeled on the Peter-Plaschet case. So essentially, there's no difference between the linear and the nonlinear case. See also these papers by Tuomo Cusi and myself, and former work by Cianchi and Mazzia and Dutzer and myself. Okay, I would like to call your attention that essentially then when there are no coefficients, actually we were able to prove that the same holds under non-uniform ellipticity assumptions. This is in two papers by Lisa Beck from Augsburg and myself, and from Cristiana De Filippis from Parma and myself. And then there are more results with quasi-convex integrants and partial regularity by Cristiana De Filippis. There's a long paper on Journal de Mathématiques Pure et Appliquée that is just appearing now. It's an extremely long and technical paper where this is adapted in the setting of partial regularity. But this is just by Cristiana herself, doesn't involve me. And also, I would like to tell that in this paper with Cristiana, that is published this year, we are able to escape these polynomial growth conditions. We are able to deal with general functions of arbitrarily exponential type. So we combine arbitrarily exponential functions. And under the assumption that the coefficients this time are a bit differentiable, so that the difference is in ln plus something, and the same condition on the right-hand side, then we prove that U is locally bounded. The idea of having Sobolev coefficients also starts from old papers by Christensen and myself, and by Eleutheri, Maskol, and Marcellini in the setting of PQ growth conditions. But here the thing is that any rate of differentiability, so any rate of Elder continuity, allows to get that U is locally bounded. So, but this is a different framework, it's just a bonus result. And this implies optimal regularity for obstacle problems of arbitrarily non-uniformly elliptic integrant. And this was also open in the literature. And this follows from a linearization methods by Fuchs and myself in the setting of PQ. So we are able to prove optimal regularity for solutions of obstacle problems, for arbitrary functions, functionals and integrants. And this is the last slide. So this is in the setting of partial regularity. This theory is being extended in the setting of systems by Tuomo Cusi and myself, but in the setting of non-uniform ellipticity, there's a new paper by Cristiana De Filippis. As I told you, it's a very long and technical paper, and you should also give a look at. And I think that's enough, and I would like to stop here. Thanks for your attention.
Okay. Yes. Are there any questions?
The cat fell asleep. Too trivial for her. That's
Hello there.
All right. So if there are no questions, then let us thank the speaker again. And back to you, Luboš, if you have some announcement for next seminars.
Thank you. Rosario, thank you very much for this beautiful talk. And
thank you.
There is some complimentary remark in the chat as well. So you should check it now because it usually disappears. It's not being recorded. Okay. I don't know, maybe it is, but I'm not sure. And yeah, there's plenty of food for thinking as usual. I think this was really a beautiful talk. Especially like so much of these references, so that it's plenty to study. We'll need a lot of time to study all this material. Thank you again. Okay, the seminar continues. Next week we have Lukas Koch from Max Planck Institute in Leipzig, and he quotes in abstract Christiana de Philippis, Senior Christensen. So it seems, I mean, these people have been quoted by Rosario several times today, right? So it seems that
I think that I in fact actually, okay, Christiania is actually quoted everywhere where this new regularity issues appear, but I actually really quoted their paper that has been in preparation for a long while, as far as I know, and it's likely going out right now, since Lucas Koch is going to talk about it. I think it's a very interesting one.
so we are still in the same ballpark, yes? So same scientific direction. Wonderful. So
Well, actually, I saw in the list of forthcoming talks, Peter Hester is going to talk also.
that's right, but
So it's likely he's going to talk about his last papers on this fact, but I actually don't know.
I think it's TBA so far, so we don't really know what he's going to talk about, but I think I saw him here today, so maybe anyway, he will tell us in time, right, what the talk is going to be about, hopefully. Okay then, so if there are no objections, I will stop the recording now.